Hi class, welcome to the second half of lecture. So we're going to talk to this part of the lecture about the weather, the atmosphere, the climate, the movement of volatiles, all of that stuff on the surface of Mars. And that's because the kind of strategy that we have for looking for life at the moment is to follow the clues left by the water. So if you pay attention to NASA Astrobiology and the NASA Mars Syndicate about what they're trying to do when they're going and exploring Mars, what they will say always they're doing is following the water, because the water is one of those essential things that we think life needs to have, and so it's our best bet that we think we have to finding evidence of life if it does exist on Mars. So we're going to talk about kind of climate and weather and evidence for water on Mars today, and then on Friday we'll use that as the springboard to search for our discussion of the search for life. So in the picture behind me today is a rendition, an artist rendition of what a warm, wet Mars would have looked like. So we think Mars in its early history was definitely warmer and wetter than it is now. We'll talk about kind of the current conditions on Mars as part of this lecture. But over time, it has lost its atmosphere, and so consequently, it lost a lot of its volatiles, and in particular, the liquid water on the surface disappeared. Now, this rendition, you'll see various renditions. We don't know what Mars of the past looked like. Mars doesn't have plate tectonics, so its continents don't shift around. So it looks certainly very much today like it did at the end of the bombardment era in the solar system. So in particular, you can see features like the Mariner Valley here. That's definitely there. The volcanoes are there. They built up long ago, and the crater life. So this is probably what a distant past Mars looked like. People who imagine that we should colonize Mars, and we can talk about the ethics of that later in the quarter, but people who think humans should invest time in transforming Mars into a more Earth-like world, terraforming Mars, as we say, this is also what you might imagine it might look like. Return Mars to the way it appeared in the past. Okay, but so this is what a distant memory of a wet Mars would have looked like. Okay, so let's start some videos, start some slides, and we'll have a little chat. So this is a scene from The Martian. We talked a little bit last half of the lecture about Mark Watney living on Mars during the movie The Martian. But I show this one here for two reasons. One is one of the things they got right about Mars in this movie is they showed that kind of layered terrain that you see there. Okay, now we certainly haven't been everywhere there is to be on Mars, but we have been some places, and Mars definitely has geology that looks familiar to us here on Earth in terms of its exposed rocks. It's got layered rocks, and the history of Mars is tied up in all of that. The second reason I show this is because one of the things they also did in this movie is they showed the weather on Mars. And the weather on Mars is largely dominated by dust and wind. Okay, now the atmosphere on Mars is not the same as the atmosphere on Earth, and the entire planet is covered in dust, and so that's kind of the way it goes. But you can certainly see in this picture that the distance is hazy. If you spend a lot of time looking at pictures from the Mars rovers, which I certainly do, then you'll see similar conditions when you look at pictures from the Mars rovers. So what we're going to do today is we'll talk a little bit about atmosphere, we'll talk a little bit about weather, and our goal here is to get to a discussion of water, because following the water is what the strategy for looking for life on Mars is going to be all about. So one of the questions I want you to think about as we go through this is, how is it that we learn about the processes that are changing the surface of Mars over time? We certainly have missions at Mars more or less continuously now. There are active rovers and active landers on the surface. They all have weather stations, monitors. But when you are presented with something that is unusual, like a picture of Mars, the question is, how do you figure out what's actually going on? And we've alluded to this as we've been discussing Mars this week. One of the ways we understand is we use our understanding of what goes on Earth in order to interpret what we see going on Mars. Okay, and so to illustrate that, here are two pictures. One of these pictures is from Earth, and one of these pictures is from Mars. And you can see they look very similar. That's because the geology, the physics, the weather of what's making the landscape look the way it is the same, similar on both planets. And so my question for you is, which one do you think is Earth and which one do you think is Mars? Okay, so I'll wait just 5 seconds here to give you a chance to not cheat and write down which one you think is Earth and Mars. Okay, so I'll count. 1 hippopotamus, 2 hippopotamus, 3 hippopotamus, 4 hippopotamus, 5 hippopotamus. Okay, did you pick one? Okay, and so the question is, did you get it right? Well, as it turns out, the one on the left is Mars, and the one on the right is the empty quarter on the Arabian Peninsula. And so what you see here are windswept dunes that are building up in the landscape, and they build up in these successive ridges, and you get these nice scallop shapes to them as the wind pushes the dunes and moves them along. Okay, so this is an example of what we call comparative planetology. We study the geology, we study the weather, we study the things going on one planet, and we use it to interpret and understand what's going on another planet. Now, what I've just described here, we're using what we know is going on Earth to try and understand what's going on Mars. But in fact, it actually goes the other way as well. There's lots of stuff going on Earth that makes understanding Earth very complicated. And sometimes it's easier to go study a simpler planet or a planet that we don't know as much about to kind of get that big picture view and then come back to Earth and try and figure out what's going on. Okay, and we'll talk about that a little bit near the end of the quarter when we talk about climate. So the Mars atmosphere is, Mars has an atmosphere, so that's certainly one of the things that makes it an important target for us in our search for life. Its atmosphere is very thin compared to what it was in the past. We think in Mars's distant past, the atmospheric pressure is maybe 3 times what it is on Earth, right? So it could have been potentially very high at some point in the past, but today it's very thin. So the surface pressure on Mars is only about 1/100th or 1/150th of what it is here on the surface of the Earth. Okay, it's mostly CO2, more than 96%. You see the NASA graphic there at the bottom. More than 96% of the Martian atmosphere is CO2. The CO2 is a greenhouse gas, but Mars is very cold. The average temperature on Mars is minus 63 degrees centigrade. So the coldest we've seen on Mars is something like minus 143. The hottest we've seen on Mars is something like 35, but the average is minus 63. So despite being a greenhouse gas, there's just not enough atmosphere to keep it warm on Mars. So Mars is very cold and is very arid as a result. The atmosphere does blow up storms. We've talked about dust storms a little bit. We'll come back to that again during this lecture. But the average wind speed on Mars is something like 10 meters per second. So that's about 22 miles per hour. That's not an uncommon or unusual wind speed that we see here on Earth. The maximum wind speed we've ever seen on Mars was measured at the Viking 1 site, which was about 60 miles per hour, about 30 meters per second. Okay? Okay. So because it has an atmosphere, all the things that you would normally expect to be associated with atmospheres happen. There are certainly storms, although they're dust storms, not rainstorms, or, well, there might be lightning storms on Mars. That's actually something we should talk about, but I didn't put in the lecture. But there are dust storms. And so the dust storms, just like dust storms on Earth, they get kicked up. The dust is in the atmosphere, and then it moves around the planet with the winds as they circulate it. And in fact, it's the heat from the sun heating the surface and then churning up the atmosphere that stirs up the dust storms to start with. Okay, but we see other phenomena as well. And in particular, we see clouds on Mars. So there is water and there is CO2 on Mars, but the clouds that we see are water ice clouds. And so they are typically very thin. We don't see those gigantic rolling cumulonimbus clouds that we see here on Earth. They're high cirrus clouds. But just like we see on Earth, they tend to gather around geologic features. So in particular, in this photo of Mars here, you see they gather around the high volcanoes. So that's places where the volcanoes stand up through the atmosphere, and then the wind carrying the atmosphere around the around the geographic feature. It rises, it cools, that causes the water to condense into clouds. Okay, so that's a process we see happen on Earth all the time. The other place where we see clouds is we see clouds in the lowland areas. And in particular, we see it in the Mariner Valley. So this is a picture of the Mariner Valley where you see the clouds have settled in, the fog has settled in and covers the Mariner Valley. That also is something we see on Earth, right? Cold air settles down into the low places. And so the valleys build up fog when that happens. So that's an example of what you're seeing here. I told you during the last half of today's lecture that Noctis Labyrinthus was one of my favorite places on Mars. And so this is fog filling Noctis Labyrinth as well. Okay. Now, another thing that we've seen on the surface of Mars at many of the sites is frost. Okay, so on Earth, when it's very cold out, so we see this in the fall and the spring here in Chicago, the land cools very rapidly because it's exposed to the open sky. And when that happens, it causes water or frost to condense on the surface of the land. Okay, so this is why your car windshield has frost on it in the mornings, is because it's cooling very rapidly to the sky. Well, so that happens on the surface of Mars. And so this is a picture from the Viking 2 site at Utopia Planitia. And you see water ice that has basically coated frost that has covered the ground and the rocks. And so at the Viking 2 site, this would start in the winter. It would persist for 100 or so days. And then when it started getting warm in the spring again, the sun would melt it away, and then it wouldn't be cold enough at night for the frost to form again. We've seen this at other sites. The most prominent site, I should have put a picture in to show you where we've seen this, is at the Phoenix landing site. So the Phoenix landing site is at high northern latitude, very close to the polar ice cap, and they also see this kind of frost behavior at the Phoenix site. I like this Viking 2 picture because I think this is the best picture I've seen of the frost on the surface. Okay. Now, we've talked about the dust storms, but one of the other things that we see on the surface of Mars are dust devils. Okay, so the dust storms happen because the sunlight heats the surface of the planet. That warm heat is radiated off, which causes the atmosphere to rise. Okay, and then as it rises, it encounters cold air, which makes it turbulent, and then that kind of stirs up the dust on the kind of large scales that we see the dust storms happening on. Similar kinds of things happen when dust devils form. Dust devils are kind of still a mystery even here on Earth, but they form in a very similar way. The vortex motion is the part that I think is hard for us to understand easily, but they are nonetheless still formed by rapidly rising air, and that causes the air to start swirling around, and it develops a very stable structure. And so you can see this top picture here is a picture of a dust devil from orbit, and then in the bottom, these are all dust devils that have photobomb pictures that the rovers have been taking. And if you look online, you can find like animated GIFs that show the dust devils moving frame through frame across the landscape behind the rovers if you go look at them. Okay, so dust devils are certainly strong evidence that you know, the winds are very active on Mars. They certainly can transport materials around Mars in the form of dust, and you can kind of see it in this top image. But another thing that NASA spends a lot of time looking at is the dust devils do leave trails across the surface, and so you can learn some stuff about the geology by studying those trails remotely. Okay. So let me return for a moment to the global elevation map. So this is the global elevation map that we looked at during the first half of the lecture today. But let me zoom in on this region right here. So this is certainly the region where Mark Watney hung out in the Martian. But I want to draw your attention to the appearance of this region. Okay, so if you look at this region, you can see these kind of deeply furrowed channels running into the region, okay, and then into the blue area, which is contiguous with the northern lowlands of the planet. You see that those channels appear to continue in these kind of wavy undulations, okay? These are exactly what fluvial flows on Earth look like, where river channels flow out into their delta regions, and where they discharge material, they develop this kind of alluvial deposit look that you see here in this image. And so this is an example, one of the kind of visual examples we have of the fact that Mars used to have a very wet past. There used to be running surface water on Mars that carved these river channels, carried sediment down the channels just like we see it do on Earth, and then deposited it where the rivers led out into the wide flat areas on the planet. Whether or not there were standing seas on Mars, that's an interesting question. That depends on how much water there was, but certainly there's the possibility for it if you see water flowing this way. Okay, so I'll remind you, these are the sites where Viking 1 landed on Chryse Planitia, which is kind of this upper left-hand side. Pathfinder landed in a place called the Ares Valley, and it's right at this outlet for this very large river channel coming from the area around the Valles Marineris. Okay, so we see this all over on Mars. You saw in the video we watched during the first half of the lecture today that we see this kind of features around the Mariner Valley. We see it here coming down off the Tharsis Bulge and into Acidalia Planitia. We see it in all kinds of places all over Mars. So this is very common, and this is one of the primary pieces of evidence that there was a wet past for Mars. So the real question is where did all the water go? And the generic answer to that question is that Mars's gravity is so low that it can't really hold on to its atmosphere. So over the course of time, its atmosphere has slowly bled off into space. And with nothing to replenish the atmosphere, the water evaporated as well. It was absorbed into the subsurface layers and into the minerals, but the water that was in the atmosphere, and certainly the standing water that was on the surface, has all been lost to space. Okay? So this is one piece of evidence for there used to be large amounts of running liquid water on the surface of Mars. Is there other evidence? And there certainly is. And here we really see the utility of sending rovers to Mars, because we can go roving around and look for evidence that water has been here. So this is what we call layered terrain. Again, in that comparative planetology sense, this is layered, and it looks exactly like layered terrain that we see here on Earth. So the upper left couple of images here show layered terrain on the surface of Mars compared to similar looking layered terrain on the surface of Earth in southern Utah. And the layered terrain that we see on Earth with this kind of geology, this kind of sandstone geology, is that it's laid down by water processes. This rock is soft, it's granular, it's made from the kind of material that we see all over on the surface of Mars, that dust and sand and grit, the Martian regolith as we call it, and it has been laid down in layer after layer by some process. The wind certainly does some of that processes, but we know water also does that process. And so that's why we're so interested in the layered terrain, and in particular, why we're interested in the layered terrain in the areas where it looks like water has flowed. That's why we put the landers down in those areas that you saw us on the last map. Over on the right here is a large frame from orbit, and so you can see these kind of sculpted hillsides where they have been carved away by processes today, weathered away by wind and so on. But you can see that as they erode away, there are definitely layers that are being exposed. Again, you can see the kind of dune-like structures that we saw in the very first image there down in the valleys between the buttes here. Okay? So we definitely look for that kind of layered terrain. Now we said that Mars is mostly an arid planet, but what we would like to know is there still water in some form somewhere on the planet? Maybe it's completely frozen like it is in the polar ice caps, but are there subsurface water? Are there warm hot springs somewhere that pushes water out to the surface and then it evaporates and we never see it? We just would like to know if there's liquid water anywhere, because if there's liquid water anywhere, then our prejudice towards the idea that life depends on water means that maybe there's life active somewhere as well. Okay, so for a long time we've been looking for this, and in 2010 we discovered these streaks in satellite images that you see right here. So this is, we see this in many places on Mars now, but this is the rim of a crater called Newton Crater. And if you kind of go a third over from the left, there's kind of a lighter band of color that goes down through the middle of the image, and you see it looks kind of streaky in a diagonal way, okay? By and large, that sort of stuff is seen all over Mars. You see these kind of streaks from the wind pushing sand around dunes and rocks and stuff like that all over the place. But here in particular, this caught our attention because we saw the image as you saw it here. But when we came back to this site and imaged it again in 2015, we discovered that the streaks had in fact changed. And so we started paying closer attention. And what we think is going on is that as the season gets warm, okay, that exposed surface there on the rim of the crater gets a lot of hot sunlight, and we think the sun may be heating the volatiles, so permafrost or subsurface ice or something that mixes and becomes very briny water, mixes with the material, and then it bursts out and cascades down the hillside here and makes a streak. So this is actually a movie. Let me play the movie so you can watch. So these are successive frames, okay? And you can see those very distinct dark areas appearing. Those appear and disappear on seasonal cycles. And so we think these are places where the subsurface water is active and induces it to be active by the fact that the sun comes along in the spring and summer and heats it up. Okay, now we're not on the surface, right? We aren't here on the surface right by Newton Crater measuring whatever that is and being able to tell that it's water. And so we don't want to fool ourselves. We're kind of diligent that way as scientists. And so we've been trying to figure out, are there other things this could be? And so one of the proposals, although I think most of us believe this is evidence for water, one of the proposals is that this is just the action of sand. So sand is a granular material, and if you've ever made a gigantic pile of sand at the beach and just kind of kept trying to pile it on top and on top, you know that it cascades down the sides and you get flows of sand that behave in many ways like a liquid. So what's been shown is that granular materials can flow and make streaky structures like this. Okay, but the real question is if this is sand and not water, why does it only happen in the spring and the summer months? Okay, and so that's still the thing that would have to be explained from that kind of model. The thing that would have to be explained from the water model is, well, how's the water surviving and what's the water supply look like, and is there any way that we can validate that this is really briny water running across the surface and then evaporating again? Okay, but nonetheless, this is potentially very interesting because this was one of the first indicators that we had that there could be liquid water close to the surface on Mars. And if we're going to look for life, that's really an important step for us. Okay, now there is one other important discovery about water, and this was just made in 2018. So we've been doing radar studies of the planet. So radar can be done from satellites in orbit. You basically ping the planet, the radar signal comes back. Now, one of the things, if you've ever read about radar, and the reading about the history of radar is actually really interesting. I can recommend some good books for those of you who are interested in that. But radar does not penetrate water very well. That's why you can't use radar to look for submarines. You got to use sonar. Okay, so water is very dense and reflective to radar beams. Okay, so here, this is an area around the North Polar ice cap, and you can see in the left-hand image over here is a set of colored streaks showing the radar passes that they made around the North Polar ice cap. So this image is actually rotated 90 degrees from, so 90 degrees counterclockwise will give you the image on the right. Okay, but the image on the right is a blow up of that radar region that you see there in the left-hand image. And what you see is right there in the middle is a triangular area, which is a very hard radar reflector. Okay, so that area is about 19 kilometers across, and it's about 1.5 kilometers below the surface of the kind of permafrost region that they're looking at here near the ice cap. And so the radar reflectivity is so hard and so centralized in a localized area. It's not some kind of pervasive geology theme that's spread around, that the supposition is this is a subterranean liquid lake. Okay, so that is potentially very exciting, and it's not unusual. We see these kinds of lakes here on Earth. Those of you who know something about your Antarctic exploration know that there's a very deep, large lake below the Antarctic ice sheet called Lake Vostok. They've drilled down into that lake. It's 3.5 kilometers below the ice sheet in Antarctica, and so this is a similar analog lake that we may have discovered below the surface of Mars. Okay, so there are many instances where we see evidence of volatiles and water moving around Mars, ranging from the ice on the polar caps to the clouds that we see condensing around the geographic features, to the kind of water bursting out of the sides of craters as they warm in the summer sun, to the evidence that we see here for these subsurface lakes. So the notion that Mars once was a weather planet is not completely absurd. There's certainly water on Mars. The notion that there is still water deposits on the planet today is also not completely absurd. We have really good evidence for that. And so we're going to lean on that to talk about the search for life next time. Okay, so that's all I'm going to say for lecture today. I hope you're all having a great week. And catch up on your reading and read a little bit more about Mars. I obviously haven't told you everything that's in chapter 8, but on Friday we'll talk about the search for life. Okay, so have a great night, everyone. We'll talk to you later.